Hey, and welcome to the second video in our series on proof, and we're going to be looking at technical proof by exhaustion in this particular video. So we did deduction in the first one, let's do exhaustion in this one. So here we go. We saw from the previous video, if we wanted to do a proof, if you're trying to prove a result, for example, we had consecutive square numbers in the previous video, trying to prove that they're always odd. If you've got an unlimited number of those, then you can't check every single example. But if there are only a limited number of examples that need to be checked, you can actually do them all. And so that's what it means by exhaustion. Exhaustion basically just checking every possible example. So here we go. Prove that all numbers between 20 and 30 includes can be written as the sum of a string of positive consecutive numbers. So all we've got to do is just basically work through all of them and see if it works for every single number that's there. So here we go. Let's start off. The easiest ones to crack to begin with are the odd numbers, because, for example, if we take 21, halve it, that's 10 and a half, and so go down half, upper half, you've got 10 plus 11. And the same idea will work with all the odd numbers. There we go. So they're the easiest ones to crack. Okay, so of the ones we've got left to do, the next ones to have a look at are the numbers that are odd when you chop them in half. So, for example, if we take 22, we can write that as 11 plus 11. And we already know that 11 can be written quite easily as a string of consecutive numbers, so that would be 5 plus 6. And then the other 11, if we just kind of chop one off the 5, add one onto the 6, we've got 4 plus 7, there you go, there's a string of consecutive numbers. So 4 plus 5 plus 6 plus 7 is 22, that's that one sorted. The same technique will work with 26, and a similar technique will also work with 30. So again, we're just kind of working through all the numbers. And then finally, if we just have a look at the ones that are left, and leave just a bit of thinking, gets us to 20 is 2 plus 3 plus 4 plus 5 plus 6. 24 turns out is 7, 8, 9. And 28, I don't know if you might have spotted that one as being a triangular number. There you go, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. There we go, done. So we had to prove that all the numbers between 20 and 30 can be written as a string of positive consecutive numbers. We've done them all. We've proved they work for all the ones we were asked to do. So there is our proof by exhaustion, so it does work. The previous one was fairly obvious because you had a list of numbers to check. In a slightly different type of proof by exhaustion, let's have a look at this one. So we've got to prove there are only two possible triangles with integer length sides that have a perimeter of 10 centimeters. So this one seems a little bit more open-ended, but again, a logical approach will get us to where we need to go. So let's just start thinking about what possible length sides we could have. And we're going to do this in a very systematic way. So if we start off with a triangle, we've got where one of those sides is 1 centimeter. So we can have 1, 1 and 8, or it could be 1, 2 and 7, 1, 3, 6, 1, 4 and 5. And of course, when we get to the next one, which would be 1, 5 and 4, we've already done that one. So we don't need to duplicate it because it's already there. So we know we've got all the triangles where at least one of the sides is 1 centimeter long. Now let's just do exactly the same as before, but now let's do it with one of the sides being 2 centimeters long. And clearly straight away we can see that one we've already done because it's a repetition of 1, 2, 7. So we've got 2, 1, 7, next will be 2, 2, 6, 2, 3, 5, 2, 4, 4. And on we go. And just keep listing them all. The next one is 3, 3, 4. And then that turns out that's all of them done. Now we need to have a look at all those possible combinations and see which ones we can actually make, because some of those will not physically make triangles. For example, if we take a look at the first one, what you've got is if one side is 8 centimeters, the other two sides are 1 centimeter each. You can see from the diagram there is no way they're going to join to be able to make a triangle. So that's why I've got the statement on the screen there saying the ones that can form a triangle, the ones that the sum of the two short sides is greater than the length of the long side. So that's what we're looking for. So we need the two smaller numbers to be bigger than the larger number. So for example, we've seen that 1, 1, 8 isn't going to work. 1, 2, 7, again, same reason, because we're going to have 7 would be the long side. Imagine that side would be 7. I'd have a 1 centimeter side, a 2 centimeter side. That's still not going to work, so that would take that one out. So we've got that one's gone. That one's not going to work. The next one is not going to work, and so on and so forth. That one, 1, 4, 5, 1 and 4 makes 5, so effectively that would just form kind of a straight line rather than a triangle. The next one, again, no to that one, no to that one. And now when we get down here, we say, well, if the longest side is 4, we've got a 2 and a 4, so that one is going to work. And again, down here, the longest side is 4, and the other two sides are 3, so that one is possible as well. So those are the only two. So again, we did it by exhaustion because we identified every single possible combination we could have, and then found the ones that actually can be made into triangles. So there's our proof done.